by I. Finally. In general, for diagonal ones, it will have the same shape of the type bar. we can draw some cylinder, but now the cylinder lifts it out to the side.
One to one.
Do we have people online? What are we?
No, this is for registration. If somebody wants to watch it,
Oh, right.
it will be put on the
Yeah.
on the website, so it's
Right.
for registration. I think that's okay. It's okay.
Okay. No echo.
No.
Great. Where were we? Yes. Lattice regularization of various things. So CFT itself, 2D critical lattice model. Or we could also make this into 1 + 1D periodic spin or anion chain. Then we have the result generators. These we can also put on lattice. These will go to so-called Cousin generators, which have been around for a while now. These will be expressed in terms of the Hamiltonian density and momentum density of the Hamiltonian of the spin or anion chain. So, in particular, we just look at the Hamiltonian and the momentum. The Hamiltonian will go as 2π over n, and being the size of the lattice or the spin chain, L0 plus L0 bar minus C/12. While if you instead take the momentum, the last momentum, this goes to 2π over n L0 minus L0 bar. This means we can extract conformal dimensions on the lattice. The primary and descendant fields will also have some correspondence on the lattice. These will go to low energy eigenstates of Hamiltonians. And finally, the goal of today is to do the same for topological defects. And these now will correspond to some impurities on the lattice. I will go in more detail what that means, but essentially in the integrable model, this will be some inhomogeneity spectral parameter. And this now, part of the story has been known for a long time. So 1S type, remember parameterizing by Katz label, is a well-known. And then we have R1, This is more recent, and this is what we really want to get at. And once you have both of these, you can get general RS type by fusion. How am I doing on time?
Well, I think you passed 20 minutes, so you have like, oh, I don't know.
Should be fine. Okay, so to show how we can construct the defects then, I need to say a bit more about the lattice. So the focus here will be integrable models based on the Temperley-Lieb algebra. And this might seem a bit restricted, but you can find a lot of models through this way. So by picking different representations of Temperley-Lieb, you can get RSS models, so you get all the minimal models, and you can also get some non-unitary models, for instance, through loop representations. And so the setup will be to construct this 2D critical lattice model row to row using a row to row transport matrix. This is now not this residential tensor transport matrix. And so this will just look like some operator going like this. And we imagine time going upwards. And then by just taking several of these and stacking them on each other, you can get some extension in time. And then you just get the partition function by tracing over this. Trace. Yeah. And T of U in turn can build out of R matrices. It will now just be one of these crosses. And these R matrices will fulfill the Yang-Baxter equation. And if they do, that in particular guarantees all the post matrices will commute TU, TB, sorry. And in our case, we'll write this R matrix in a particular form. Or J, just putting positions on this chain, would be some sign. Identity, sign, EJ, but EJ will now be something that fulfills the Temperley-Lieb relations. So EJ squared EJ J minus 1 J that's back EJ. And this you can show graphically, so you can represent EJ as the average time going upwards as just some couple gap. And these relations are then saying that if you stack both these together, just do just the price of loop weight, or you have some line going like this, you can just control this property. Yes, and just straighten the line. And we do this. And we'll draw our matrix. I'm going to draw it now with time going a bit like this because it makes it nicer to draw. So then R. Sorry. Oh. Yes, yes, there is. So wait. B will be 2 cosine gamma. And we usually parameterize this. So you have this Q that will be e to I gamma. And so this gamma, the choice of gamma will depend on the model. And then U is just a spectral parameter. Yeah. Okay, so if we draw R in terms of these, we'll get sine gamma minus U, something that goes one way. If we try to go like this, plus sine U, something that looks like this. If we now take T of 0, this will just be translation. So this will just translate to. And then you can get your Hamiltonian. So you can take this their inverse, T U. This will be H. This will be just proportional to sum over EJ. This will just look like some sum of terms like this. And now if we start inserting representations, so for instance, the Ising model representation, then we would recover the usual Ising model Hamiltonian, which for the lack of time, I'm not going to write out, but happy to write that later. And now we want to use all of this to get the defects. Would it be helpful if I write out the Ising Hamiltonian, or is everyone happy with it? Everyone's happy. The way now that we do the construction is in the direct channel. Which I remind you is the one where we go in the time direction. We will just start changing U, the spectral parameter, at one position, and then we do this for each row. So we keep going up in time. So this will give us an impurity Hamiltonian. Where some part of the Hamiltonian will look slightly different from the other parts. And if we do this, this will change the spectrum of the Hamiltonian. So it will modify H and H bar. And that's what we expect, because we know that this defect should act like fusion. And so we should have some different parameters going. Or we can recross the channel. This is the one where we're now going around. And as you might guess, we're doing now is we're putting the same impurity along all of the transfer matrix, but we're only doing it for one row. And then we go back to the usual transfer matrix. And if we do this, this will act as an operator. We'll give some eigenvalue, and this is what we have seen that this defect should cause. This one up here. So one particularly nice choice of changing the spectral parameter is as follows. I will mark this, I will call Rj of U plus Vj, this is the homogeneity. And we'll take J, IV, and we're sending V to plus minus infinity. And the reason this is nice is that if we do this, Rj turns into a braid representation of braid group. So we get Rj as we take V to infinity, V Gj, which we can look at for this, or it goes to minus infinity J inverse, which will draw like this. And of course, this is nice because now if we start doing this and we build up our critical lattice model, we suddenly have one line that decouples from the others. So now, in the 2D system, we get something that looks like this one line that just goes either above or below all the other lines, or vice versa if you do this in the cross channel, the other line that decouples there. Or you can put this into the Hamiltonian, and then you will get the usual sum. But you also get some new term. So it's minus Ej, Ej plus 1, J inverse, or inverse here, regular there, depending on which direction you go. And so you will get some term that goes like this. And again, it's clear that this line is now decoupling, and so you have something that is topological already on the lattice. You can move it freely across the other. So, line decouples. And now again, if you insert the Ising representation everywhere here, this extra term actually gives you exactly the duality defect Hamiltonian of Ising. So I'll just write this Ising duality defect, which is in 1, 2. And you can try again, you can insert some other representation. So let's say you insert the Potts representation, then you get a similar defect for the Potts model, which again acts as a duality defect. So you will, cancel some transversal field, you will update a bit some interactions. And so more generally, this will give you a 1-2 type defect. So the less type defect. And for the last part, and we get to the actually interesting part, which is how we use that to get to an R-type defect.
How do you see that it gives you a statement?
But how we see that it gets, so you can see it in different ways. So I don't think I will have time to go through the various checks, but you can, for instance, look at the spectrum. You can look at the entanglement entropy, you can measure various things to see that this corresponds to a 1-2 defect. Like either you do it in the direct channel, you see how it modifies the spectrum, the new conformal weights. And you do this for different models, you see that it's always consistent with 1-2. Or you do it in the cross channel, you check the eigenvalues. Or you do it, again in the direct channel, you compute entanglement entropy. Yeah. So generally, this gives us a small 2. And even more generally, you could get any one S by putting several of these together and fusing them, or just take some, higher spin in here. And so next up is R1 and especially 2-1. And again, it will generalize. How long do I have for the last part? How long do I have to for the last part?
You're already like 40 minutes, maybe conclude 5 minutes.
5 minutes? Yeah, I think I can figure it out in 5. Plus or minus. Okay. So the last part is defect flow, starting at 1, 2. So this is really the new part. So we have seen 2 types of defects that we can put. We've seen Vj to plus minus infinity. This gives us a 1, 2. And we've also seen the trivial one. I mean, if we don't put anything else, that's a trivial defect, right? So Vj equals to 0. That's a 1, 1 defect. And now the question is, what happens in between? And what you can do is you can expand your Hamiltonian around this defect. And if you do this, skipping over some details for lack of time, you will get something that looks like the Hamiltonian, so the one that you started with, so 1, 2 defect Hamiltonian of e to the minus 2v, the same parameterization as we had somewhere before. Something else, right? Which we will interpret in the continuum as a perturbed Hamiltonian with some coupling. So think of this as h equals to h1, 2 plus some coupling times some perturbed v. Right. And we can note that the dimension of gamma to the 1 over dimension of the field minus 1 is really L. So we will define some length scale from this. We'll just call this now our length scale. And then we're going to plot different quantities against the system size divided by this length scale. And if we do this and we actually have the correct dimension for this field, we'll get a scaling collapse. And then we know what this perturbation is. And then we can try to do some other perturbation to get to something else than a trivial one. That's the general idea here. And so I will try to draw numerical plots on the blackboard. Let's take the example of the Ising model, and let's get maybe some colors going. So let's say we're plotting h plus h bar of the ground state, which is something we can extract from the Hamiltonian. Right? We start at 1, 2 defect. So this should be 1 over 16. We should add up at 0. And now if we start doing this, and start plotting data points with a large value of v, can do some intermediate values, and finally we can do some v equals to 0, and we get this very nice scaling collapse if we choose a very particular dimension for this operator. So if phi is either 1 plus phi1 3 or phi1 3 plus 1, then we get this nice scaling collapse. And what I'm plotting against here is this n over r I with delta being the 1 by 1. And so now we can ask, okay, did we just try different fields until we got it right and we got scaling collapse? The answer is no, this is a well-studied perturbation. This is very nice work by Komosa and Watts. Where you have a 1-2 field perturbed by either this operator or that operator. So we have 1, 2 perturbed by some combination of these. So you have I1, 3 cross identity, or there's some other part. And they draw this very nice diagram depending on the sign of these couplings. So you start with 1, 2, would be your R, your O. If you go in this direction, you end up, well, let me start. If you go in this direction, you end up with 1. If you go in this direction, you end up with 1, 1. So that's what we have seen before. We can go between the trivial and the 1-2 defect. But if you go in the other directions, you get 2, 1. So if you can change the sign of your coupling, you can get instead of the trivial defect, you get to 1, which is what we want to get to. And then there are some other points that they get to, some new defect, some additional defects. These we're not especially interested in. But the whole point here is, okay, we want to change the sign here. If we do that, we're done. We have R-type defects just by going in the flow in the other direction. So that's the very final thing I want to say is how do we change the sign? And then I'm done. So we identified this coupling that we also called big number at some point. This was e to the minus 2b, ej, ab. So change sign is actually very easy. B going to b plus 5 pi over 2. That's all we need to do. And in particular, we can get to the very end of the flow. We can get to 1 just by taking R minus pi over 2. Or if we want to do it as a transfer matrix, you can make this defect in the cross channel. So crossed to 1 t minus pi over 2. Or we can do direct. Then we will get some impurity Hamiltonian. H1 will be the usual one plus some a new term ej plus 1 plus ej plus 1 ej. And again, we can start inserting representations here and get well-known defects. So if we do Ising representation, we get the well-known energy defect, which we know is 2 dollars. And so just to finally complete the picture, we can, go the other way around in this diagram. We now start adding this I_2. We do this for large values of V. We can do it for some intermediate values. Okay, go all the way to 0. And then in this example, ending up at 1/8, which is exactly the one we should get for the two-bond defect. And more generally, we can construct different defect defects, and we can go from those. We can go from 1 as either s minus 1, which was the trivial path in the 1-2 example, or we can go to S1, so we can get an R-type defect. And that's the construction. We now have all the defects. Thank you.
Okay, other questions?
About this cross channel where you say T of minus pi/2, so can you draw that in terms of these loops? Maybe then?
This one doesn't look nice, right? So unlike the 1-2 defects, these are not topological on the lattice. So you don't get this nice decoupling of the line or anything like this. It will just look like some terrible combination of Temperley-Lieb.
Okay, so
Can you elaborate for those who doesn't know? Can you formulate some defects in terms of temporary algebra? You mentioned temporary algebra, and